In this video, we're going to go through a steady-state open system practice problem. And so in this problem, what we're analyzing is an adiabatic steady-state turbine. The inlet to the turbine is steam, which is at a temperature of 600 degrees Celsius and a pressure of 10 bars. And the mass flow rate, we're told, is 2.5 kilograms per second. All right, and the inlet to the pipe also has a diameter of 10 centimeters. The outlet of the turbine is at a temperature of 400 degrees Celsius and a pressure of 1 bar. Right? And the outlet pipe diameter is going to be 25 centimeters. And so with that information, what the problem wants us to do is it wants us to estimate the work rate that could be extracted from this turbine. So based on the information in the practice problem, what I want you to do is pause the video here, and I want you to identify what the goal of this problem is, and I also want you to use this information to sketch out a process flow diagram. Okay, and so using this practice problem, what we're going to do is in order to solve these problems in thermodynamics, we need to be systematic. So we're going to go through each of the steps of the sort of guideline that I gave for solving thermodynamic problems. Okay? All right, and so step one of the steps was to read the problem statement and then identify the goal of the problem, what the problem wants you to solve for. Okay? And so in this problem, what we want to do is we want to calculate the work rate that we could obtain from this turbine. Can be obtained from turbine. And also, one thing we should look out for that the problem statement sort of emphasizes is that we're dealing with steam, and the steam is expanded in this turbine. Okay? So that's step one. Identify what the problem wants you to actually solve for. Step two is now we're going to, based on the information in the problem statement, we need to sketch out a process flow diagram. Okay? And so in our process flow diagram, we're going to have a turbine, and we're going to have some inlet, which I'll denote as stream 1, and some outlet, which I'll denote as stream 2. In stream 1, we have some mass flow rate of 2.5 kilograms per second. The temperature is 600 degrees Celsius. The pressure is 10 bar, which is the same thing as 1 megapascal. And the diameter is 10 centimeters. For the outlet of the pipe, the information we know is that the temperature is 400 degrees Celsius. The pressure is 1 bar, which is the same thing as 0.1 megapascals. And the diameter is now 25 centimeters. As far as things we don't know, we're not explicitly told the mass flow rate that's leaving, and in the end what we want to figure out is the amount of work, or in other words, the shaft work that could be extracted from this turbine. Okay? Alright, so now that we've sketched out a process flow diagram and sort of identified all of our knowns and unknowns, let's do a little bit of accounting. Alright, and so now that we've identified that we have two unknowns we need to solve for, what that means is we need two equations. We need to derive two equations that we could use. Alright, so for every unknown that you have, that means you need another equation in order to solve for all of the unknowns. Okay? Alright, so we have two unknowns and two equations. And before we start employing our different sorts of material and energy balances, we want to make some assumptions in order to simplify the analysis. Okay? And so for this problem statement, based on the fact that we have mass going into and out of the system, what we're going to do is we're going to treat this as an open system. that's one assumption we're going to make. For our second assumption, we're treating this as an open system, and we're given a mass flow rate here, and all the values that we're given, they're not changing as a function of time. Right? And so another assumption we can make is that the system we're dealing with is at steady state. In fact, let me write that out. It's going to be at steady state. So that's an assumption we're going to make. And mathematically, the way that manifests is that in our material balance and our energy balances, any sort of accumulation term is going to be equal to 0. Okay? For our third assumption, we're told in the problem statement that the system we're dealing with is adiabatic. It also tells us it's steady state. So the system we're dealing with is adiabatic. And so if a system is adiabatic, that means the heat flow rate into the system is 0. Okay? Alright, so those are some of the assumptions we're going to make. But another thing that we need to account for in this step, or to think about before we start using our balances, is what is the reference state going to be of the species in our system? Alright? And so if we remember, what we're dealing with in the system is steam that's expanded in this turbine. Okay? And so, since we're dealing with steam, we know that, from MEB2, we have entire sorts of data tables that contain thermodynamic information about steam. Or in other words, we could use the steam tables to get things like enthalpies, internal energies, or specific volumes. Okay? And so, since we're going to be using those to get our thermodynamic properties, what that means is that the reference state we'll use for the steam in our problem, that's going to be the reference state. We're going to use the same reference state as the actual steam tables themselves. Okay? Alright, and so, if you remember, in the steam tables, they typically use the triple point of water as the reference state. And so what that means is that our reference temperature is going to be 0.01 Celsius. Our reference pressure is going to be 0.6113 kilopascals. You can convert that into megapascals if you want. And the reference phase is going to be water in the liquid phase. Alright? Okay, so that's all the information that we need to think about before we actually start applying our balances. Now that we've gone through our assumptions, identified our unknowns, and identified our reference state, let's now start going through our balances. So that's going to be step 5. Alright, and so the order that I always recommend in proceeding is start with your material balance first, then go to your energy balance, and as we'll see later on in this course, we'll then start using something known as an entropy balance. But for now, we'll just stick to material and energy balances. Alright? Okay, and so let's first start with our material balance. So let's do a material balance on steam. Alright, and in our material balance, what should always start out with is accumulations equal to input minus output plus generation minus consumption. In this problem statement, we're not dealing with any reaction, so there's no generation or consumption. And also, as we talked about in our assumptions, the system is at steady state. So accumulation is going to be equal to 0 as well. And so what we get is that for this system, the input is going to be equal to the output. From our process flow diagram, we know that our input mass is just equal to m1 dot. We know that our output mass is equal to m2. Therefore, what we get is that m2 is going to be equal to m1. And we know know that that value is 2.5 kilograms per second. All right, so that's essentially the first equation that we used. So remember, we had two unknowns, we needed two equations. One of our unknowns was M2, and so by using just our material balance equation, we were able to solve for M2. Okay, all right, so that means we got rid of one of our unknowns, so we have one unknown left. So then our next step should be to go to the energy balance. All right, and since we're dealing with an open system, we should use the open system form of the energy balance. All right, so in the open system form of the energy balance, we have dE dt is equal to, if we expand out the energy term on the left-hand side, we could expand it into an internal energy, and a kinetic energy, and potential energy terms. All right, so this is a change of energy in the system. The right-hand side now is going to account for the energy transfer terms. And so that includes the heat rate, the shaft work rate, which is what we're going to want in the end. And then we're also going to account for essentially the energy of things going into and out of the system. And so the way we're going to write it is like this. Okay, where m is the mass flow rate of a species going either into or out of the system. This alpha here, remember, it just tells you, just depends on whether the stream is going into or out of the system. If it's into the system, it's positive. If it's out of the system, it's negative. And then for each of these streams that are either going into or out of the system, they're going to carry with them some enthalpy, some kinetic energy, and some potential energy. Okay. All right, so this is our energy balance. But before we proceed, we could start making some simplifying assumptions, or we could start simplifying the equation based on the assumptions that we talked about earlier. So these things. All right. So once again, our system is at steady state. And so that means that, the energy of the system is not changing over time. And so these terms over here on the left-hand side, which are, essentially saying how does the energy change over time, if the total energy is remaining the same, that means that all these terms go away. They're zero, because steady state. We're also dealing with an adiabatic turbine, so once again, that means Q dot is going to be equal to 0. And the other thing is, in this problem statement, we're told, that the piping changes diameter, but there's really not any information in this problem statement about the, the steam changing height or anything, as it goes into or out of the system. So as a result, there probably isn't any sort of potential energy changes that we need to worry about. Okay, so we're going to get rid of that term. All right, so we knocked out a bunch of terms from our energy balance, and so let's write out what remains. 0 is equal to shaft work, and then now let's expand out the summation. So let's first talk about the things going into the system. Right, 1 squared. And now let's talk about things going out of the system, and because the stream is going out, it's going to be negative. Okay? All right, and so in the end, what we want is WS. Okay? And so essentially, of the two equations we needed, this is going to be our second equation. All right. But before we can get WS, there's some other values that we need as well. We need that, the enthalpy and the velocity of stream 1. And we also need the specific enthalpy and the velocity of stream 2. Okay? And the way we're going to figure those out are going to be from the steam tables, like I talked about earlier. Okay?